Welcome back. We're now ready to take a look at the symmetric property. This property, just like the reflexive property, operates on the set A. So we say that a reflexive property, a relation on a set has the reflexive property when an element relates to another element, that they can also they still relate to one another when you swap their order. Now this is not always going to be true. It may seem, well, if X relates to Y, then they're related, and so Y relates to X. But we only need to check the condition that if X relates to Y, is it also true that Y relates to X? So it may not be the case that every element relates to every other element, but for the ones that do relate to another element, can we switch the relationship, the order of the relationship, and is that still an element of R? Okay, so let's go ahead and take a look at our set A with the elements 1, 2, 3, and 4. We're going to say that the relation holds on two elements if those two elements are equal to one another. And we've also already listed out the set of all elements that are in this relation, 1, 1, 2, 2, 3, 3, and 4, 4, because those are the only pairs in which the X and the Y are exactly the same. So here's our little diagram of the mappings of the elements from set A back to set A. And in this case, we would need to see, does one element ever relate to another element? That's not the case. An element only relates to itself. So the premise of this statement suggests that only for elements that relate to other elements do we need to worry about, does the other element relate back to the first element. So we don't see any elements related to other elements, and therefore the symmetric property does indeed hold, because this is just conditional upon, does an element relate to another element? So since that's not the case for any of the elements in set A, we would say that there's no violation of this principle, and therefore we could argue that the following. We could say, since X only relates to itself, since an element only relates to itself, R has the symmetric property. So in other words, the only time that we would ever need to worry about a relation not having the symmetric property is if one of these elements were to relate to another one. For example, if 1 related to 3, then what we would expect to see is that 3 also relates back to 1. So if this were the picture, then we would have to evaluate, okay, 1 relates to 3, does 3 also relate to 1? Yes, it does. Therefore, we should see inside of the set that if 1, 3 would be in there, that 3, 1 would also be in there. But since there's no mapping from one element to other elements, there's no violation of the symmetric property, and we say that the relation does have the symmetric feature. That may seem kind of counterintuitive because there's nothing really to check, and in that case, since there's no violation of it, you're all good. So for example, if you are driving and it's required that you have a driver's license when you're driving, and you don't have a driver's license, but you're not driving, then there's no violation, right? You don't have to have a driver's license in general unless you are driving. So if you are driving, then you must have a driver's license. If you are not driving, then it doesn't matter. Let's take a look at the next one. So what we're looking at here, we do have elements related to other elements. So for instance, we have 1 relates to 2, and we see that by this arrow right here. But does 2 relate to 1? Is 2, 1 an element of that set? Well, since 2, 1 is not an element of that set, and in the schematic, since 2 does not point back to 1, that would mean that 2, 1 would be in the set. Since 1, 2 is in there, we already have a violation because 2, 1 is not. So we don't need to go any further than that, because if we have one violation, it doesn't matter if, for example, 1, 3 were in there, and then 3, 1 was in there. If we did have an arrow going back to 1 like this, we've still already violated the symmetric property on at least one of the ordered pairs, Therefore, this would not have the symmetric property. So since the ordered pair 1, 2 is in the relation, but 2, 1 is not in the relation, well, by definition, this does not have, R does not have the reflexive property, the symmetric property. R is not symmetric. So in the schematic, we should see that if an element of a node points to another node, then that other node should point back to the first node for all such pairings. Now we can also look at the differences between elements. For all elements x, y, if x minus y is even, then that's going to be an element in the set. Now we didn't list, well, we did list out, we listed out all the pairs right here. So I need to map through this, and let's just go ahead and draw this picture again so that we can really clearly see whether or not this is going to have the reflexive. Symmetric, excuse me. So it does have the reflexive because 1, 1, 2, 2, 3, 3, and 4, 4 are all elements of the relation. But we also see here that 1 relates to 3. So I'm going to use a different color here. I'm going to say 1 relates to 3. And does 3 relate to 1? Yes, it does. That means since 1 minus 3 is negative 2, and that's even, 3 minus 1 is positive 2. That's just the same number, different sign, and that's also going to be even. So 3 minus 1 is even. 3, 1 is in the set. I can proceed in the same fashion. I see 2, 4 is in the set. Is 4, 2 in the set? Okay, so 2 relates to 4. Oh, there it is. 4 relates to 2 since 4 minus 2 is an even number as well. So we're good so far. So we have 1, 3, we have 2, 4, and we have 3, 1, and 4, 2. I think we've covered all of our bases here. And since for every element that maps to another element, since that other element maps back to the first, since we have arrows going both ways, we are going to conclude since for all x, y in the relation, yx is also in that relation, R is symmetric. Great. So that's perfect when you can list out all the elements. When you're checking for the symmetric property or any of these, you have to kind of do this all-encompassing thing where you say, is it going to be true for every single situation? Well, let's take a look. M is the set of all discrete math students in our class, and we're going to relate two people in that class if person 1 has the same grade as person 2. Now, I wasn't clear here last time. Of course, I would want to say where M1 and M2 are both elements of students in our discrete math class. Now, I can't really draw this diagram, but I can ask the question. Let's say that I have some element here, and I'm going to refer to this element as M1. If there's another element in here, which I'll call M2, let's just suppose that M1 has the same grade as M2. Okay, so that means if, let's say, M1 has an A, or M2 has an A, and M1 has the same grade as M2, that means M1 also has an A. Well, can we say it in reverse? Can we say that M2 has the same grade as M1? Well, yes, because they both have A's or they both have B's. So for M1 to have the same grade as M2, that means M2 has the same grade as M1. It's just a matter of switching the two names around. If Bill has the same grade as Sally, then Sally has the same grade as Bill. And reversing those two elements in that sentence does not change the fact they both have the same grade. So if M1 has the same grade as M2, then it's, almost like kind of obvious, I guess. M2 has the same grade as M1. And therefore, and this is going to be true for all M1, M2 in the relation. Perfect. So that means R is symmetric. All right, one more. P is a set of all people in the world. We're going to define two people to be related in the kind of the real, like, related sense if X is a sibling of Y. So let's just say again, let's try to establish this. If X is an element in this set and X is a sibling of Y, okay, so that means that X and Y are going to be siblings. So we're considering all people in the world. That means that there are going to be some people who have a sibling, right? Not everybody is going to, and we don't have to worry about those people. We only have to worry about those people where X is a sibling of Y. Is it true that Y is a sibling of X? Well, yes. I mean, just because I say that Joe is my brother, Joe can't say he's not my brother, because if we are in fact brothers, then it goes both ways. So this means that we're also going to have Y is a sibling of X. So since X is a sibling of Y, then Y is a sibling of X for all such pairs in the relation. Therefore, R is symmetric. And that's the symmetric property. Now again, just one thing to make evident here is we only have to worry about situations where we have elements where one element relates to a different element. Then it must also work in reverse. In situations where there is no element paired with a different element, then as long as that property is not violated, we can still say that that relation has the symmetric property.